Hello, welcome to my presentation. I'm Xueyang, and I finished my doctoral study at ETH Zurich under Professor Dick Moore. And today my topic would be using machine learning-based methods to model the rate and temperature-dependent plasticity and fracture response of engineering metals. And without further ado, let's go into the background. And why do we look at the strain rate and temperature effect of engineering metals? Let's take automotive industry, for instance. And on the left-hand side, it's an overview of a 2022 Porsche 911. The body in white is still mostly steel and aluminum alloys, as you can see. And their rate and temperature dependency are very critical in not only in the crashworthiness analysis, but also in the manufacturing of the load carrying components. And popular one would be hot stamping and hot forming, which is a prime example of high temperature but low speed or intermediate speed operation. Of course, the demand for a better model comes not only from automotive industry, but also from other industries. For instance, aerospace industry would look at low temperature, but high strain rate response of materials. And let's be a bit more specific. And what really motivates us to look into advanced high-strength steels? These automotive steels. On the left-hand side is the data from the famous paper of Johnson Cook. Here I plot the true stress, true strain curve from 4043 steel and Armco iron. You see that, as expected, with the increase in temperature, there is a drop in the flow stress. People usually refer to this as the monotonic thermal softening. However, this is not the case for advanced high-strength steels, automotive steels. On the right-hand side is the force displacement curve of a notch tension test on a sheet metal DP780 at quadrastatic loading speed. This is a test at 20 degrees C. If we increase to 100 degrees C, there's a drop in force. If we increase to 150, the force kind of plateaus here. 200, almost the same level. But if we look at 300 degrees C, the reaction force is even higher than the 20 degrees C curve. And people usually refer to this as dynamic strain aging effect due to some microstructure. And popular models like the Johnson-Cook model is actually not able to capture this effect. And we see this effect not only in DP780, but in all the DPs that we have tested, DP800, DP980, DP590, and even in some third generation steels, medium magnesium steels. And of course, we tested not only at low strain rates, but also at high strain rates. Here's an overview of NT20 test at intermediate loading speeds. On the left-hand side, I show the measurements from infrared camera. In the middle is the measurement from the high-speed optical camera at 2000 fps. On the right-hand side, I show the history of temperature and history of force. This is a test starting at 200 degrees C at intermediate loading speed. Now let's perform the test. We see that once the test starts, before the necking, we have a slow but constant temperature rise. And as the necking develops, as we reach the force maximum, there is a higher and higher slope of temperature rise with a terminal temperature reaching 260 degrees C, so 60 degrees Kelvin higher than the start. And this is a process of converting the plastic work into heat during the dynamic event, and we will come back to that later. If we want to test at higher loading speeds, we have to go to other systems. For instance, here we use a SHPP system, split Hopkinson pressure bar system. And we use a very compact system and where the striker would have a compressive loading on the input bar, and the load inversion device would convert the compressive loading into a tensile loading on our sheet metal specimen. We use an induction coil on the top of the specimen to heat up the temperature, to heat up the specimen into the target temperature. The reaction forces can be measured on the signal from the out gauges taped to the output bar. This is a typical example of the signal we get. I would say it's on the cleaner side. Now that we have these experiments performed, how do we model this rather complex strain rate and temperature behavior? In this case, we developed a machine learning-based plasticity model. Here we combine the Hill 48 equivalent stress with a non-associated flow rule. We treat the material as isotropic hardening, decomposing into the flow resistance into two terms. One term is the room temperature quadrastatic hardening response, which we take as the reference term. And just like Johnson-Cook model, we give it a multiplier. The multiplier would be a neural network. This neural network would take the strain rate, temperature, and aging time as input, and output a scaling factor that scales the room temperature hardening response into the target strain rate and target temperature. And there's an extra term of aging time here that we took from Professor Chabot's paper in 2013 that deals with the dynamic string aging effect. To train this neural network, there are a couple of things to keep in mind. We write the neural network into a user subroutine in Abacus explicit, and we calibrate it using an inverse analysis type of method to deal with the convergence issue in the electroplastic subroutine. We use a counterexample regularization technique to control the strain rate sensitivity. All these details will be found in our papers. And we have talked about so much about model building, model structure. How does the model perform? On the left-hand side is the trained force displacement curve. Dots are experiments, solid lines are simulations. The curves are shifted each by 1 kilonewton for better visibility. These are the slow tests that last around 5 minutes. We see that our model performs very well, marking the large deformation post-necking response for all the temperatures. Same holds true if we move on to intermediate speed tests, lasting about 0.3 seconds, and high-speed tests performed on the SHPB system, lasting around 1 millisecond. And now that if we focus on one test, the intermediate 200°C test that you saw in the video previously, as we perform a couple thermomechanical simulation, we are able to reconstruct the temperature field in our numerical simulation, and we see that we match exactly the temperature distribution as well as the peak temperature during the test. And now that we have our model, we could also apply it not just to automotive steel, but other metals, other engineering metals. In this case, we had a look at a broad range of tests for 7000 serial aluminum at a wide range of temperature and wide range of strain rate. On the left-hand side, I compare the experiment and simulated force displacement curves at low strain rates. You see from room temperature to 300°C, we have a very good fit, especially at high temperature, large deformation, post-necking response of the material. Same holds true for intermediate loading speed. This is 100 times faster than the slow one. Second intermediate loading speed, which is 20 times faster than the previous one, and high loading speed performed on an SHPB system, targeting a strain rate of around 100 per second. And it's worth noting that instead of HU48 plus yield surface, for aluminum alloy, we can also combine the model with U2000 yield surfaces. So the model framework is actually rather flexible. Now that we have trained our hardening model, we can easily visualize it in 3D. Here I plot the flow stress as a function of strain rate and equivalent plastic strain for selected temperatures, starting from room temperature to higher temperatures. On the left-hand side is the hardening curve of DP780. On the right-hand side is the hardening response of 7000 serial aluminum. We see that despite the difference in the material, in the microstructure, completely different materials, completely different hardening responses, we can use the same framework to model it. And neither of these framework, in fact, neither of these materials can be modeled using Johnson-Cook model. Now that we have looked at the plasticity response of these materials, we can now focus on fracture. Here we just have a look at the ductile fracture, the initiation of ductile fracture. This is where we introduce the concept of loading paths, which is the history of material point from the start of plasticity formation all the way to the onset of fracture. We extract these loading paths, these histories, from the numerical simulations where the onset of fracture takes place. Well, unfortunately, in material characterization tests, we cannot have constant stress states. Basically, we cannot have constant loading passes. Why is that? For instance, if we take unexo tensile tests, for instance, once we have necking, inside the neck, the stress state, the triaxial and load angle parameter values deviate from unexo tension states. And also, same for the UT test inside the necking would induce a localization, which would give a rise in the strain rate. And at dynamic events, in dynamic loading speeds, And conversion of plastic work into heat would also cause a change in temperature. To deal with this complex strain rate, temperature, and stress state effect, we extend the Hossford-Coulomb fracture model. The essence of Hossford-Coulomb fracture model is just a stress state-dependent fracture initiation model that deals with the first 3 dimensions of this 5-dimension space. And then, what do we deal with the strain rate and temperature? In this case, we can employ another neural network. This neural network will deal with the rest of the 2 dimensions. The neural network will take the strain rate and temperature as input and export the Hossford-Coulomb model parameter at this specific strain rate and temperature. The Hossford-Coulomb model, the analytical model, would then take these model parameters and predict the fracture strain at this strain rate and temperature under proportional loading. And the advantage here is that instead of doing a model in 5D space, the neural network can control the strain rate and temperature dependency, while the stress state dependency is controlled in an orderly fashion by the Hossford-Coulomb fracture model. And we use a linear damage accumulation to account for non-proportional loading, and these models can be optimized using full loading parties. Now let's have a look at how the network adapts itself during the training. On the left-hand side, I do the epochs, meaning the iterations in the training. I plot the equivalent plastic strain as a function of stress triaxiality for tests starting at 180 degrees C for 7,000 serial aluminums. We tested many different geometries: shear, central hole, NT20, NT6, and many different strain rates. Now let's do our optimization. The dots here represent our neural network model prediction, and solid lines are the loading parties that we extract from our numerical simulations. We see that as the training goes, the dots approach the end of the lines, meaning that fit is getting better and better. What is more interesting is on the right-hand side. Right-hand side, I plot the fracture load C for 180 degrees C at 4 different loading speeds. You see that as the network is getting trained, the network identifies a higher ductility for low loading speed and low ductility for higher strain rate. And we didn't tell this to the network, it identifies this by itself. And in the end, after a couple of epochs, we reach a mean absolute error on damage around 8%. And it is worth noting that here the damage is the damage indicator going from 0 to 1, with 1 being fracture. And now that we have trained our fracture model, it is possible to actually visualize the fracture strain for different stress states. For instance, here I plot the fracture strain as a function of strain rate and temperature for shear stress state, inertial tension, equal biaxial tension, and plane strain tension stress state. And due to the analytical formulation of a Hossford-Coulomb fracture model, inertial tension and equal biaxial tension have the same fracture strain. What we can see at the first glance is that the material is most ductile at high temperature, 350 degrees C, and the quasi-static loading speeds around 0.01 per second for all load stress states. And the fracture strain seems to increase with temperature and decrease with the strain rate. This is rather intuitive. And you might have some doubts. I mean, you have the neural network, you have these many parameters, how do you really use it in industrial applications? And it is actually quite straightforward. One could extract lookup tables for industrial applications to accelerate the numerical simulation instead of solving the full neural network backpropagation and front propagation equations. An example of this is that we have implemented the model through the GIGS framework in LS-DYNA, and it works quite well. With that, I will conclude my presentation today, split into 2 parts. For the first part, we had a look at the strain rate and temperature dependent of the engineering metals. We started with DP steels, non-monotonic temperature effects, but the model still works very well for large deformation at aluminum alloys, And results can be found in our 2 papers if you scan the QR code. And for the second part of my presentation, we look at the fracture initiation problem at different strain rates and temperatures. We propose a neural network-based fracture model that can be trained using evolving loading parties. So we do not request a constant temperature, constant strain rate, constant stress state. We do not request that. And the stress state dependency can be constrained by the analytical Hossford-Coulomb model, while the strain rate and temperature dependency can be easily controlled by the neural network. And with that, I will conclude my presentation. Thank you very much.